So in this lesson, we're going to take a look at the tangent problem. And our goals here are that by the end of this lesson, we should be able to find the slope of the tangent to a function at a particular point. And we should also take that one step further and be able to find the equation of the tangent to a function at a point. Now you might ask yourself, what do we mean by the tangent problem? Well, the tangent problem is basically just this question right here. How do we find the slope of the tangent to a function at some point? Because we saw in the last lesson that the slope of the tangent to some function at a point represents the instantaneous rate of change of that function at that point. So if we want to find instantaneous rates of change, we want to find slopes of tangents. So here's our situation. Okay, we've got some function, and it can be any old function at all. We'll call it f at x. Okay, and we want to find the slope of the tangent to this function f at x at some point. And let's just say that the point that we want to find it, the point where we want to find the slope of the tangent is the point, we'll say x equals a. Okay, rather than putting in a number, we'll just put in this value a here. So we've got, let's say, x equals a is right there. So this is the point where we want to find the slope of this tangent to this curve. Okay? And if we were to go ahead and calculate the y value would just be f at a. We can just find that using the function. Now, how do we find the slope of the tangent, or how do we find an instantaneous rate of change? Well, we want to start by considering the slope of the secant between this point, a, and some other point. So we want to find the slope of the secant line from, let's say, a to some other point which we are going to call x. So we pick some other value of x, which we're actually going to call x. Okay. Then we draw the secant line from a to x. Okay. So this point here is going to be x f at x. Okay. We can calculate the y coordinate just using that function. And what we are going to do is the slope of this secant line, obviously, is delta y over delta x, or our change in y, so f at x minus f at a. So the difference between those two y values divided by the difference between those two x values. So that's just our formula for the average rate of change from the last lesson, where here we're using a function f instead of a function s, and we're using x instead of t. How do we get the slope of our tangent? Well, the slope of the tangent at a is going to be, well, we take this point x and we're going to move it closer and closer to a, sort of along here like this, and this secant line that we've drawn is going to become closer and closer to our tangent line. So we want to take the limit as we make x closer and closer to a of this formula here for the slope of our secant. So f at x minus f at a all over x minus a. That's what we want to do. Okay? So sort of like put a box around this. Okay? Because next up we're just going to do an example where we use that formula there to find the slope of the tangent. Okay? So remember, what we're really doing is we're taking a series of slopes of secants and we're looking for the value that everything is tending towards. So here's the kind of question you might be asked to do. Okay? Find the equation of the tangent to the curve f at x equals negative x squared plus 4x plus 1 at the point x equals 3. So let's first try to visualize what's going on in this question. We've got some function, f at x, which is a parabola that opens down. We'll call this f at x. We've got a point that we're interested in, x equals 3. And at this point, we want to find the equation of the tangent to that curve. So the tangent to the curve, of course, is always a line. So we know that its equation is always going to have the form, good old y equals mx plus b, that you've been using since grade 9. So if we are going to find the equation of a tangent, or the equation of a line, we need two things. We need the slope, and we need a point on that line. So which is easier to find? Well, I think the point on the line is easier to find, because we've got the equation, we've got an x value, we can just take our x value and sub it in to figure out what our y value is. So we're going to say that our a value here, we're using on the last page, is going to be 3. Okay? X equals 3 is the point that we are interested in finding the tangent at. So a equals 3. So let's evaluate f at 3 here. Negative 3 squared plus 4 times 3 plus 1 gives us, we work this all out, we end up with 4. So our point that is on the curve is the point 3, 4. We can label that in our diagram here, 3, 4. So this point, where our tangent and our curve meet here, is called the point of tangency. Now we need to find the slope. And this is where that formula from the last slide is going to come in handy. To get our slope, we are going to take the limit as x goes to a of f at x minus f at a all over x minus a. Okay? The limiting value of the slopes of the secants as we move this value x closer and closer to this value a. So if a equals 3, we're really finding the limit as x tends to 3 of f at x minus f at 3 all over x minus 3. Okay. As we move x closer and closer and closer to 3. So how can we do this? Well, we're going to have to set up a table here. So we're going to have a column for our x value. We're going to have a column for our a value, or the point that we're interested in finding the slope of the tangent at. We're going to calculate f at x. We're going to calculate f at a. And finally, we're going to calculate f at x minus f at a all over x minus a. So our a value is going to be 3. That's not going to change. And we're going to choose x values that are close to 3, but get closer and closer as we go along. So 3.1, 3.01, 3.001. Okay. And we're going to evaluate our function both at x and at f at a. Well, f at a is not going to change. So it's going to be 4, 4, 4, no matter what we do. f at x is going to change as we change the value of x, moving it closer and closer to a. So we'll get something like 3.79, 3.9799, and 3.99799. So you might want to keep 5, maybe 6 decimal places when you're doing some of these calculations. Our final column here, slope of our secant, this is the one that we're really interested in. So if we do f at x minus f at a divided by x minus a, for our first row we get negative 2.1. Second row we get negative 2.01. Third row we get negative 2.001. So when we look at the final column of this table, what is our estimate for the slope of the tangent at x equals 3? What do these numbers seem to be heading towards? Negative 2. So our slope is the limit as x tends to 3 of, I'll just write delta f at x divided by delta x, which equals negative 2. So this is our value for the slope of the tangent at x equals 3. Now we've got to take this one step further because they were asking us for the equation of the tangent. We know it's going to have the form y equals mx plus b, and we already know a lot of these things that appear in this equation. We know that our slope is negative 2 because we just worked that out. We know that when our x value is 3, our y value is 4 because we calculated that point that was on our tangent, or that point of tangency which is on our tangent and is on our original function. So the only thing we have left to find is this value for the y-intercept, b, which is pretty easy. 4 equals negative 6 plus b, so b must equal 10. So the equation of our tangent is y equals negative 2x plus 10. And there we are done. Okay. So the most time-consuming part of this question is setting up that table to find the value of the slope of the tangent, or that instantaneous rate of change. And over the next couple of lessons, we're going to look at ways that we can make that step a little bit quicker. And then when we get to the next unit, we're going to look at how you can make it a lot quicker.